This episode is brought to you by World Anvil. Here on SFIA, we like to say that if brute force isn't working, you are just not using enough. If a spaceship propelled by detonating nuclear bombs doesn't count, I don't know what would. So welcome to 2022 and the start of our 8th season here on Science and Futurism with Isaac Arthur, and I'm your host, Isaac Arthur. I thought we should start the dawn of this new year by looking at the first spaceship design that offered a realistic chance of sending a human colony to a new solar system alive and intact. That is Project Orion, initiated in the 1950s, and we will ask what upgrades and modifications modern technology might make Project Orion even better. So we will be focused on essentially 4 things today. First, a brief explanation of how Project Orion works, along with an equally brief tour of our history of it and some of its sibling projects. Second, how to scale it up to be bigger and more efficient. Third, how to scale it way down to be cheaper and more viable to launch. And fourth, some hybrid scenarios, like using atomic bombs to slow a ship at the destination, but pushing beams or lasers to speed it up. Now, the entire Orion project revolves around a few pivotal concepts. The first of those is that whether we're talking fission or fusion, or even matter-to-energy conversion like antimatter, the power involved at the nuclear level is millions to billions of times higher than what chemical fuels release. As an example, almost every chemical fuel, or best modern batteries for that matter, is somewhere in the tens to low hundreds of millions of joules per kilogram. Body fat, for instance, is about 37 megajoules per kilogram, sugar and carbs about 17 megajoules, gasoline about 44, whereas a kilogram of uranium fuel runs about 1 million times that range, fusion loosely about 10 million, and matter-to-energy conversion is roughly 1 billion times denser than chemical fuels, at 90 million billion joules per kilogram, from Einstein's famous E = mc squared. To bring that into focus, Little Boy, the bomb dropped on Hiroshima in 1945, released 63 trillion joules of energy on detonation and weighed just under 5 tons at 4,400 kilograms, or 14.3 gigajoules per kilogram. That includes all the housing and conventional explosives in the bomb, which was a very primitive and inefficient device, and yet it still pushed out 100 times the energy per kilogram that hydrogen fuel could have, almost energy-dense chemical rocket fuel. This led to being seriously contemplated as a possible spaceship propellant as early as 1946 by Stanislaw Ulam, the co-designer of the first thermonuclear weapons with Edward Teller, though the notion had been played with before, even written about by sci-fi juggernaut Robert Heinlein in his 1940 short story Blow-Ups Happen, that somewhat predicted fission bombs before the Manhattan Project even began. This leads to problem 2. Nuclear bombs are awesome power sources but give their energy off way too fast, in a near-instantaneous detonation, whereas nuclear reactors propel a spaceship by using their awesome power to either heat up a gas and shoot out the back, or to generate electricity for running something like an ion drive, to magnetically propel an ion stream out the back or generate a beam of light that acts as your rocket flame. You obviously lose a lot of efficiency converting the nuclear reaction to electricity and have a lot of heavy equipment you have to carry around for that task, but an electric ion drive or photon rocket can make for a very good spaceship. Another option would be superheating a gas to use as a propellant. This certainly works to create an engine better than a classic chemical rocket, but not by as much as you'd think from those million-fold energy densities, because the entire reactor and any exchange materials had to be built from real materials, which melt at certain temperatures. It's hard to get a rocket flame to temperatures of 10,000 Kelvin if your entire apparatus melts at 2,000 Kelvin, and the hotter the gas, the faster it pushes a rocket. Nuclear level temperatures permitting ships to reach fractions of light speed tend to involve temperatures of millions of Kelvin, like we find in the cores of stars where nuclear fusion occurs. The smaller the atom or molecule serving as propellant, and the hotter it is, the faster a rocket can go by using it. Hydrogen atoms coming out at stellar temperatures are something we can produce, and something that lets you make ships propelled by them get up to reasonable interstellar speeds. Unfortunately, we can't rapidly produce them inside ships or reactors without melting them, and we basically produce them by setting off a nuclear bomb, which is something you usually would not want occurring in or near your spaceship. It tends to void the warranty. This was all well known to scientists at the time working with the notion of nuclear reactors on spaceships. There were no treaties about nukes in space at the time, and we worried less about radiation safety back then. Nuclear engines looked good, but not nearly as good as a bomb would. See our episode The Nuclear Option for more discussion of where the science led there, with ion drives and photon rockets. Now, Project Orion came later, but for the next decade the notion of using nuclear spaceships got explored a lot, especially with the development of the hydrogen bomb, the first of which, Ivy Mike, massed a huge 74,000 kilograms, 17 times as much as Little Boy, but generated an incredible 10.4 megatons of explosion, 700 times more than Little Boy. As a reminder, many of these devices weigh tons, but we measure explosive yield in the equivalent weight of TNT, 10,400,000 tons in this last case, mini packed supertankers worth. It can get a bit confusing at times, which is why I often use joules of energy instead. The Mark 21 bomb design, famous from Castle Bravo's TX-21 Shrimp, would mass a mere 8,000 kilograms and have a yield of 18 megatons, 75 million billion joules, 1,200 times the yield of Little Boy for less than half the mass of the overall device. That is nearly 10 trillion joules per kilogram of total nuclear device, 100,000 times better than our rocket fuels. The entire Apollo 16 mission, the most fuel-heavy Apollo mission, came in around 30 trillion joules, or just 3 kilograms worth of that nuclear device. And since most of an orbital rocket's launch's fuel is going into lifting its own fuel, basically a kilogram of nuclear device will let you get a modest-sized spaceship to and from the moon on 1 kilogram of bomb. With two obvious problems. First, detonating bombs in our atmosphere is politically and ecologically non-viable. Since most of a rocket's fuel is for getting out of that atmosphere, a chemical rocket and a second nuclear device for use further from Earth is less awesome as an option, though still very handy. Second, and it's the big one, we can't really make a 1 kilogram nuclear bomb, and we can't make it detonate slowly over a period of a few hours. Now, we can actually make bombs in that size zone, but we'll come back to that later. Nuclear bombs generally are way more efficient the bigger they are, more energy per kilogram of fuel and device, making for higher final speeds and by large margins. The smallest nuclear device ever actually made, the Mark 54, was a single kiloton device, weighed only 51 pounds or 23 kilograms, and that's only a yield of 180 gigajoules per kilogram, better than Little Boy, but only about 2% of Shrimp and other thermonuclear bombs of the 50s. Nonetheless, that's still more than 1,000 times energy denser than even hydrogen rocket fuel, and a single kiloton bomb is a lot more viable as a fuel. How does this get done? Inside an atmosphere, you're trying to ride a shockwave, but up in space your bomb is producing a ton of gamma radiation, which is only getting absorbed by the device, not the air around it, so there's no real shockwave, just a massive release of radiation akin to a neutron bomb. So you need a great big tough and massive shield behind your ship to protect you from the radiation and convert that radiation into kinetic energy. This is where the pusher plate, or various accordion designs or front-mounted parachute designs come in to absorb the blast, then convert that violent jerk into a slow push or pull on the actual main inhabited part of the ship. Or basically, the blast kicks the pusher plate forward into a giant spring system, which then slowly relaxes back into place, and that near-instant hit translates into several seconds of acceleration up in the crew module. We'll get to ways to improve that, but the basic idea then is that you detonate the bomb as close to the pusher plate as you can without breaking it so as to waste as little of the blast as possible, and you just rinse and repeat. Closer is better, and a bigger pusher plate in width lets you detonate further away while absorbing more blast, but the plate needs to be strong too. Operation Plumb Bob, for instance, tested this concept with a 1-ton steel plate pushed by nuclear blast under it, after which they never found the plate. This is where Project Orion comes in, headed up by Ted Taylor and Freeman Dyson, who any channel regular knows the work of, as he's a legend on this show. But their project came in 1958 and 5 years later ended with the signing of the Partial Test Ban Treaty of 1963. That treaty might have greatly aided the mission of peace, but sadly did a lot to limit nuclear research. We could devote an entire episode to just discussing that project, and Curious Droid did a good video on that topic a few years back. The report released by General Atomics in 1959 offered 3 basic sizes of Orion spacecraft: the Satellite, the Mid-Range, and the Super Orion, massing 300 tons, 1 to 2,000 tons, and 8 million tons for each. Needless to say, that latter is eye-poppingly large, 8 million tons of ship and fuel, and it is suitable for an interstellar arc ship and is the version most often being referenced, along with various improvements that were added later. It's thousands of times more massive than the Satellite or Mid-Range, and tends to grab all the focus from the public and sci-fi writers. Those other smaller versions, though, tend to get more interest for folks actually in the field because they're a lot more practical and might actually get funded in their lifetimes. Many other in-between sizes of ship were also proposed at various times, including some designed to launch from Earth itself into orbit, which are very economical ways to move a ship from Earth to other planets using only atomic bombs, but we will bypass those today because while they might see use on other planets for early colonization periods, I just can't see us using them on Earth. Mind you, launching Orion ships on Earth is not some cataclysmic event, but I think we would only be okay with testing, building, and using these if we were expecting a cataclysmic event. Like we need to get people off Earth to some other world before a doomsday here occurred. This is also essentially what the Super Orion design is for, though it is typically envisioned as being assembled and launched from orbit or far from Earth. Super Orion designs might permit us to move whole cities to other solar systems at about 1% light speed, but we don't need to move that many folks or go that fast to get around the solar system, and Super Orion ships cost on the order of the entire US economy for a year to build, at least circa the 1950s. The smaller ones cost way less and work very well for colonizing our own solar system from infrastructure on the moon and in Earth orbit and cislunar development. While tests were done, obviously it didn't get built in their lifetimes for the folks on Project Orion. That 1963 treaty basically ended the project. Things shifted to more of a theoretical basis since experimentation was heavily curtailed. Nonetheless, at this point we have a spaceship engine and design that could permit relatively fast missions from Earth's orbital volume to other planets, and even to other solar systems. It's not been built, it's expensive, it's big, but it's all entirely proven concepts, and we have a lot of areas we have gotten better at in the 60 years since the project shut down, and that's what I want to focus on. One big thing folks often argue against is that since it's nuclear bombs, folks will never be okay with such a ship being built. I hear where they're coming from, but that's a very generation and cultural specific viewpoint. They can be handled fairly safely so long as you limit the ships to not coming closer to Earth than geostationary with actual control of those bombs, and for the tiny yield ones, even low orbit unauthorized use is not exactly cataclysmic, though definitely a good reason to have orbital defenses and intense monitoring in place. One option that might help too would be the Project Medusa approach, which replaces the pusher plate to the rear with a giant sail to the front that the nuke gets detonated in and the ship gets pulled by a tether. This lets you detonate nukes further from the actual planet while the ship is still in low orbit or even stationary, like it was sailing off a space tower or orbital ring. Such tethers could potentially be thousands of kilometers long, coming in from angles like cords on a parachute. Folks might feel more comfortable with nuclear ships in cislunar space if the detonations were only occurring above geostationary, and you could potentially have the nuclear magazine and launcher kept outside that space too. The bombs for use further from Earth could be sent by railgun from orbit or the moon to rendezvous with the ship once it's safely far from Earth, or even sent as multiple packets. It's not that I think folks would ever come to love nuclear bombs and feel safe around them. It's more that I think we'll be comfortable using them constructively when every country has them, and any asteroid miner with the right 3D printer gear and robots can spit some fission bombs out without anyone knowing. Building nukes in secret on Earth in your basement is a lot harder to hide. I am hardly a fan of encouraging nations to build nuclear arsenals, but I generally see the approach of preventing nuclear proliferation as a losing strategy in the long term, though effective currently. If they are much more available, then all the fields of their legitimate use resulting in proliferation are redundant, and you might as well use them for productive ends, since doing so no longer increases the risk of anyone getting them for destructive ends. There are a ton of productive uses of nukes too, besides for spaceships. Indeed, our entire episode on high-tech search and rescue was written on a dare that I could come up with a valid reason to use nukes in search and rescue, and I did not come up with a single reason. I came up with 4. So the smaller ones might have a role in colonizing the solar system, and so let's examine improving those first. As mentioned, Project Orion is the big original project, but there were a lot of successors who worked on it without being able to do any testing. One is Minimag Orion, or Miniature Magnetic Orion, from around the turn of the century that suggested doing fission with a magnetic field compressing the fissile material. Normal reactors are slow, and nukes are fast because we rapidly compress the fissile materials so that every neutron made gets sucked into neighboring compressed uranium or plutonium to cause a chain reaction in microseconds. Every neutron emitter and absorber is closer together, so virtually every neutron is absorbed, and quickly. This causes the explosion. However, a magnetically compressed fissile material might let you bridge the gap between slow reactor and hyperfast bombs. Most of the way to smaller bombs is the conventional chemical explosive used to detonate them, and discussions of minimum critical mass are always in the context of such implosions. Expected yields would be as low as 50 gigajoules, about 4 seconds worth of the power emitted by rockets during the launch of the old shuttles, and about a dozen tons of TNT equivalent, rather than the 1,000 tons or kiloton TNT equivalents of smaller nuclear bombs. You can make a much smaller Orion device, and potentially a pretty efficient one, for a fission-only version by being able to bypass all the chemical explosives and the sizes needed for critical mass of a conventional nuclear bomb. Now, I love Minimag and would love to see it get developed more. It holds a lot of promise as both a propulsion system and a weapon system, and could potentially be ramped up to creating micro-fusion bombs too. But development of it is probably not going to get a lot of interest in funding in the near future, as it's not really super tempting as a power supply. It also runs parallel to a lot of looks at using magnetic confinement for fusion too, so I think it will get explored, but sadly not sooner than later. It's got a lot of potential. Magnetic confinement or compression of fusion fuel is also present in Project Daedalus and Longshot variations. Another approach is to use bombs just to make them a lot smaller. Suitcase nukes are mostly a myth. The W-54 warhead was still 23 kilograms and easily detectable, so not something you'll sneak in a classic suitcase, but we can make them smaller. We've pretty much maxed out conventional explosives, but nukes are made out of weapons-grade uranium or plutonium mostly because of cost. There is more to fission than uranium-235 or plutonium-239, as we looked at in the Future of Fission and its companion episode, The Future of Thorium, and last I checked, Californium-252 had the lowest critical mass, at 2.7 kilograms, versus 10 kilograms for plutonium-239 and 50 for uranium-235. Californium-252 only has a half-life of 31 months, and has been made by first making curium from uranium-238, which is fairly expensive at hundreds of thousands of dollars per kilogram. But then you have to turn that curium into Californium-250 by alpha bombardment, then into 252 by further neutron bombardment, so very expensive to produce currently compared to U-235 or plutonium, but that could change. As a reminder, aluminum used to be hugely expensive, rivaling precious metals, then we made cans out of it when it got cheaper. One problem though is that bombs using materials with short half-lives might not work well for an interstellar ship, since its bombs will decay before arriving and thus can't be used to slow the ship down. Uranium-233 incidentally has a critical mass of only 15 kilograms, which is the reason that sometimes comes up as a worry in concerns about thorium for nuclear proliferation. Certain technological pathways might make U-233 very easy to produce and refine, which might make it very handy as an alternative to plutonium or U-235 for off-world nuclear power and propulsion scenarios. Now there's a couple other things that could make lightweight Orion variations viable, but some also work for the bigger version too. As an example, the basic pusher plate design is a big flat plate on a big huge spring or accordion system because, frankly, that is a system which is hard to screw up and can take a lot of abuse and still work. which is handy for something you are repeatedly nuking. The upside of a big metal plate is any of its surface vaporized off in a given detonation is basically acting as a rocket flame, giving it some push too. Alternatively, something more like a piston head shoved by the blast into a cylinder of gas, which compresses and slows it, is very susceptible to pressure compromises and leaks busting out. But that is an option, and so for that matter, in the very big version, even larger than Super Orion, is detonating the bomb inside a big pot of gas that blasts out the back of the ship as a rocket burst. As we'll see when we get to enlarging the Orion design, at big enough scales, even a nuclear blast is simply no different than the little explosions in your car engine that drive the pistons. Incidentally, you can use excess bombs as a normal power source, though most of the time your best approach is to either recycle the fissile material into a normal power plant or for fusion, set the bombs off in enormous underground cavities that are scaled up pistons basically, or use a molten salt working fluid to detonate the bomb in. This concept was explored more in Project Pacer in the 1970s, but I can really only see it being used in a case like an Orion-style spaceship moving at about 1% light speed or less, either being used for Oort cloud settlement or deciding it needed to stop mid-journey and instead settle some deep space ice ball like a dwarf or a rogue planet instead of continuing on to a solar system with a nice sun providing solar power. I wouldn't rule that out though. The thing about Super Orion scale ships is they are often envisioned as gambles to save humanity from something ruining our solar system, and some hastily built version without prototyping, sailing through deep space at 0.5% of light speed, needs 1,000 years to get to even Alpha Centauri. So spotting some rogue planet with extractable resources partway through that journey would seem very likely to result in a detour, and powering that colony or temporary base on Solar obviously isn't an option at that point, whereas it is fairly easy to dig big underground piston cylinders inside low-gravity bodies like a dwarf planet. One other scenario for small ships is antimatter catalyzed fusion, which requires a source of antimatter and a way to safely store it. But if you can produce and store it, then tiny little bits of antimatter can be used to catalyze much larger fusion explosions, letting you translate micrograms of antimatter into multigram fusion explosions, producing yields that are still manageable like the Minimag approach. For raw efficiency, a pusher plate can also be replaced with something more akin to a parabolic dish, where the detonation happens at the focal point of the reflector. This incidentally lets you use nukes for ridiculously high power focused communications. It's not really ideal for propulsion since the point of the pusher plate is to absorb the blast while slamming forward, but a combination of plate and adjacent parabolic dish could be used to let you gather up energy released on perpendiculars to the ship's direction of motion for other uses, like maintaining electricity. This also parallels the forward parachute approach we see with the Medusa variant. An awful lot of all this energy is being lost as heat too, such as in that big spring setup, and that can potentially be reused for electricity, or even re-emitted somewhat directionally to add thrust. Heat in space can be moved around a ship normally by convection and conduction, big radiator systems, but can only leave the ship by radiating away as infrared photons, or visible light if hot enough. And you may be able to arrange your radiators to spit more photons out in one direction than in the reverse direction, providing net thrust. Now, as I said earlier, we have contemplated using nuclear reactors to power light production as a rocket engine. This is a photon rocket, and photons of light do indeed have momentum and can push a ship. This is exactly what you're doing with gamma radiation with those bombs in the pusher plate. It would work even better if we had a material which reflected gamma rays instead of just absorbing them, but we do not at this time, and I'd be rather skeptical about their creation. When a photon hits something and gets absorbed, that object gets the photon's momentum added to it, slowing it or speeding it. When instead the photon reflects, it heads back in the opposite direction with the same but opposite momentum, and the thing it hits will have absorbed twice the momentum instead. So reflecting photons is preferable when they come from an outside source like the sun or a laser or a nuclear blast. Laser propulsion is of interest to us, and we will come back to it shortly as a means of enhancing a normal Orion drive, but we have something called a bomb-pumped laser, which is basically a single-use laser powered by a nuclear detonation, which can become as something reflectable rather than gamma rays. One of perfect efficiency could be dropped out behind a spacecraft, detonated, and have its beam hit the pusher plate or sail and bounce off. which is at least an order of magnitude better in terms of proportion than detonating a bomb behind a plate that absorbs it. You won't get anything even close to that efficiency, but for hypothetical discussion, it seems worthy of note, and bomb-pumped lasers were a major feature of Project Excalibur, an X-ray laser system intended for ballistic missile defense. X-rays are also hard to directly reflect, but we do have some tricks that would permit us to use it this way, and so too, in a big enough ship you could just do bomb-pumped laser out the back of it, though firing a laser from a ship as a means of propulsion does not allow you to reflect it and gain that extra momentum, which hardly matters if it's gamma and you cannot reflect it anyway. Now those pusher plates are slowly losing layers of material with each blast vaporizing some off, and it may be made of layers, which raises some hybrid options. As an example, a pusher plate made of many layers of graphene would have something like 1 billion sheets per meter of plate thickness, and pusher plates are definitely things made in meters of thickness, not thin sheets. However, much as a book can be thick while paper is thin, we might imagine a solar sail many kilometers wide for reflecting sunlight or outside light beams that could be forwarded up to serve as the much smaller pusher plate. And these things are both massive affairs compared to the payloads of their ships, so getting double duty out of one makes a lot of sense. A solar sail setup like Project Medusa potentially works well with a pushing laser, but a foldable solar sail that could be squeezed into a pusher plate after being used could let you push that ship to far beyond Earth before it began using its bombs, using solar-powered orbital lasers to create pushing beams, which can also probably be used to tear that ship apart if the folks on board start contemplating wicked uses for their bombs instead of as a fuel. Hitting a ship with a beam gives you lots of options, including ridiculously high resolution and high-powered scans of the space between you and it, and nearby, in case they decide to machine gun their nukes back home to Earth, and you can just vaporize them en route back, the bombs and the rogue ship both. Nice added safety feature, but instead we could use that big sail and lasers to skip the bombs in the first step, accelerating the ships to a higher speed before using bombs to either speed up a bit more or entirely to slow down at the destination. This lets you use time-sensitive, tamper-proof detonators on your nukes too. Indeed, you could use a small Orion craft near the end as a vanguard for your Super Orion ship to carry a big solar array into the destination star system to power a pushing laser to help slow the big main ship or fleet down. Fleets also offer the option of doing things like firing a nuclear device out of a railgun from one ship to go behind another, if for instance a vanguard ship was running low on warheads as it slowed. We explored this and other types of tandem use approaches, like with lasers and with Orion and with Fusion, in our Generation Ship series, Episode 2, Exodus Fleet. That series talks a lot more about generation ships, building, flying, and living on them, and even scaling up Orion-style ships to run on things like artificial novae or supernovae. Now, can we do Orion today? Yes, absolutely, and frankly I think it's past time we modify the various testing treaties to at least allow joint testing of atomics for propulsion off-Earth. There's a lot of reasons, some valid and some not, for worrying about the safety or viability of an Orion approach to propulsion, but they are the only propulsion system we currently have that could definitely be built and definitely allow us to get to another star system, or do a real full-fledged sustainable colony on another planet in our own system in short order. It's also the best approach for handling Dino Killer and bigger asteroids, especially as one could machine gun its excess H-bomb fuel into the asteroid in question. But it can't be used for none of those roles if we haven't got real hands-on experimental data and prototyping. Alright, to close out for the day, how big could we plausibly make an Orion-sized ship these days and how would it run? I would say a total crash project, of the kind we sometimes envision if we expected the end of the world, and people unified to work on it, might allow us to throw together something on the smaller O'Neill cylinder side of things, running on supplies of fissile fuel for interior life support, that could probably let us get 100,000 people off toward a solar system, or maybe half a dozen scaled down ones of only a few thousand each sent to multiple solar systems, combined with solar-powered pushing lasers to get them moving to perhaps 5% of light speed. In a more controlled fashion, same basic tech but deployed decades from now when we have a developed orbital infrastructure and resources coming in from the moon and or near asteroids, we could probably be launching a few of these 8 megaton Super Orions a year. However, let me note that a cylinder habitat built with some durability in mind is probably running on about a megaton per square kilometer of interior area, and is likely to make up only about 10% of the ship's overall mass, since you've got the bombs and the shielding and the plates and probably hydroponics in no or slow rotating smaller stations. So honestly, if we're talking an interstellar Ark ship intended to bring, say, 10,000 people in suburban style, with lots of that used for ecosystems and zoo space, then think on an order of a few kilotons of ship per person, and only a couple thousand folks on a Super Orion. Those absolutely scale up though, and again we get better efficiency the bigger our nuke and the bigger our ship. So my hunch would be that a Super Orion would be the small and bargain size for an interstellar Ark. Not so much for interplanetary colonies or trading vessels, though big megafreighters trying to bring ice in from deep space to Mars for instance might dwarf even interstellar Arks. And you can move big icy bodies by careful Orion-style detonation of nukes on one too. Will we ever see them? Very hard to say. There's an assumption that almost any scenario that gets us working fusion as a power source would make the Orion concept obsolete, but that's not necessarily true. A big and efficient fusion plant might not transfer into one that could be used in Starship propulsion or anything smaller, but might be awesome for creating transuranic elements like Californium-252 on the cheap, or for simply upgunning your economy so much you could churn out the ships and bombs to run them. In either scenario, or if fusion turns out to be that technology that's 20 years in the future and always stays on that distant horizon, then the Orion spaceship concept, with some modifications, is the one that will take us to the stars. And it can do it too. The same nuclear bombs that scared whole generations into fearing the end of our world and the twilight of our species may hold the keys to humanity seeing the dawn rise on a million alien worlds. So we are into a new year now and we have some announcements, notes, and episode schedule that we'll get to in a bit, but one of those notes is on just how much information we had to cut out of today's script just to get it short enough for a single, long episode. Another part of that though was how many other things came to mind as I wrote the script, and one of those was that not only can nuclear bombs potentially take us to new worlds, they can also be used to help us forge them too. And we'll be examining that topic with a focus on nuking Mars to us blue and green at the end of this month. Speaking of forging new worlds though, odds are good if you're a show regular, you spent a lot of time daydreaming about strange new worlds and peoples, and maybe tried your hand at writing some science fiction or fantasy, or have played an RPG like D&D or modded a video game. If not, they are great ways to spend the winter months cooped up inside but with your mind soaring to strange new worlds of your own construction. But if you have, then you probably have had that world-building effort grow in complexity till you needed notes and wanted to share it with others, and probably been frustrated by how much time got spent organizing those, or learning some software to help develop them, or maybe even lost them. I doubt it would surprise any show regulars that I've experienced that a lot myself, and always wish there was good world-building software that was easy to learn and comprehensive. And when I first saw World Anvil, the award-winning world-building toolset, I was both amazed someone finally made that software and irritated my own gaming group was going on hiatus. But it didn't stop me from exploring all the features like map notes and map connecting, history, timeline and genealogy building, and wiki-like crafting options. It's great for DMs and folks wanting to let their audiences peek into a novel setting more collaboratively, as it does have a free version and also has ways to monetize your content on platforms like Patreon, Ko-fi, or your own storefront. And you can share that content selectively to keep the secret content hidden. They also have an amazing collection of great tutorial videos, so not only can you learn how to use World Anvil, but so can anyone you're trying to introduce to it, though it's very intuitive. World Anvil offers Wikipedia-like articles for your world setting, interactive maps, timelines, an RPG campaign manager, and a full novel writing software. All the tools you'll need to run your RPG campaign or write your novel, and never lose your notes again. If you'd like to give World Anvil a try, and let it help you forge new worlds, just click the link in this episode's description. I was mentioning my gaming group going on extended hiatus a moment ago, and I wanted to give a shout out to my best friend Bill on the birth of his first daughter Evelyn in December. Bill and I served together in the army and have been like brothers since 2004, and us and some other close friends used to play D&D back then even when we were in Iraq, and he and I kept that up even when he got out to go to college to become a history teacher, and still do to this day. I was contemplating on that 18-year friendship, how much he and a lot of my other army brothers helped shape this show, as so many of the concepts and examples I've used in episodes here got crafted and honed, chatting about those ideas with them. There are a lot of folks who helped make this show in one fashion or another, and this episode in particular is one such example, as we have a lot of forums and groups either directly attached to this show or loosely affiliated, and one of those approached me around a year back about this topic, and I suggested they might try writing a collaborative outline or draft. And they did, and it was comprehensive and ran some 30 pages. I didn't even try trimming that down in favor of writing from scratch with the paper fresh in my head, and it really drove home to me how much more we could do on this topic, and also how grateful I am for getting to work with so many amazing and talented folks, not just on this episode or this show, but down the decades. Speaking of more on this topic, we will be having that episode on nuking Mars Green at the end of this month, and one on nuclear transmutation in March that I just got done recording. But we have plenty more topics for this month, beginning next Thursday with a return to the Alien Civilization series to look at the concept of civilizations going into hibernation. Then we'll be having our mid-month Sci-Fi Sunday episode on the classic sci-fi trope of telepathy. After that, we return to the Civilizations at the End of Time series for a look at the Big Rip, the cosmological model that might see the universe torn to shreds trillions of times sooner than we normally expect things to end. Now, if you want alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode, please hit the like button, share it with others, and leave comments below. You can also join the conversation on any of our social media forums, find our audio-only versions of the show, or donate to support future episodes. And all those options and more are listed in the links in the episode description. Until next time, thanks for watching, and have a great new year.